Have you ever wanted to put up an antenna with no radials, but for one reason or another, you couldn't do it? But you didn't you didn't want the radials because of space limitations or something else. Well, what we're going to look at today is an antenna right here that does not require radials. It's resonant on 20 meters. It is currently 42 feet tall. It's fed at, I think, around 26 feet is where the feed point is. And we're going to look at this and how it's constructed and how it performed. As you'll notice, about 10 foot above the ground, there's a ferrite core. We're going to talk about that and the purpose of the ferrite core. It's a 43 mix. It's got about 12 wraps of coax around it, and it is a requirement for this antenna. What we're going to compare it to, let me back up so we can get a little bit better look. See if I can back it up and we get a little better look here. There's the top down to the base. What we're comparing it to is a quarter wave ground mounted vertical with 8 radials, resonant for the 20 meter band. So both of these are 20 meter band antennas. This one is a quarter wave. This one is a half wave. And we're going to talk about these in detail. So let's go inside and talk about how it's constructed to begin with. Let's talk about how the antenna is constructed. It's made basically out of coax. I did a video on this previously, a antenna for the 10 meter band, and this one is for 20. But what you have is you basically have a quarter wave section from the center conductor and a quarter wave section from the shielded side. And there's two options. You can either strip back the coax and use the insulated center conductor for 16 foot 4 inches, or what I did was I took a piece of wire and I made the wire resonant for 20 meters, the center of the 20 meter band, and I used that and I soldered it onto the coax right here at the center conductor. Then you have a shielded portion matching your upper portion, and you may have to adjust the length one way or another depending on the type of coax cable that you're using and the velocity factor. But in my case, it worked out 16 feet 4 inches. Once you get to here, you wrap around, what I did was wrapped around 12 loops or 12 passes through a ferrite torrid core. It's a 43 mix core, 240-43. And what this does, this stops the currents from coming down to your transceiver. So how does this thing work? It's essentially a dipole. You have two sides of your dipole and it's oriented vertically. What your ferrite core does right here is it stops the common mode current that the antenna is using on this part of the shielded section from going down into your transceiver. So I think on the previous one that I made, I used 10 turns for the 10 meter band. It just so happened that I used 12 turns on this one right here based on some manufacturer's suggested instructions. I think it came from Palomar Engineering. I don't recall exactly. But that's how it is constructed. You have a section of center conductor, 16 feet 4 inches long, a section of the shielded coax, the coax shield, 16 foot 4 inches long, as the other side of your dipole, which is essentially what this is. 12 turns through a ferrite core. I use 43 mix. You can probably get away with 31, but it's wrapped basically like this right here. This is for something else. This is not related to this antenna, but same principle. And then whatever it takes to go down to your transceiver. So we've talked about how it's constructed. What was the SWR I could get out of this? Well, 1.7 to 1 is the best I could get. That matches up also with the previous one that I made for 10 meters. So 1.7 is about the best I could get. I could make adjustments down here to the length of the shielded coax portion by adding a turn or removing a turn. Either way, it would start, the SWR would start to rise. It would rise up to 1.8 with just a couple of inches one way or the other, shifting this core one way or the other, up or down. So SWR about the best I could get, 1.7, but that matches the previous build that we did. How does it perform? Well, compared to the quarter wave vertical, and depending on the contact that you're making and how far away they are, it seems to vary. Basically, someplace 200-300 miles away, you lose 3 S points on your meter, your S meter. If they're, let's say, 600-700 miles away, you lose 1 to 2 S points. So it does not perform as well on close range as a quarter wave vertical. But because of how the radiation pattern is for this vertical dipole as compared to a quarter wave ground mounted vertical, the DX radiation pattern seems to be better. You get more low angle radiation off of this. For example, this morning I did not join the net, but there was a net going on and they had a contact from South Africa. And I could hear the guy from South Africa on this antenna better than I could the quarter wave ground mounted vertical. So it seems that this is a more, I think you'd say probably a more efficient antenna for DX contacts than it would be for something local, say 200 to 300 miles away, because of the radiation pattern. So how does it perform? Well, it depends. It depends on what your purpose is and what you're trying to do, as it does with any antenna. So is it worth the effort to build? Well, if you need a antenna that has no radials, it's a single vertical, no radials required, yeah, this might be the thing for you, because you can still make contacts, they can still hear you. You may not break through a pileup as well as you would with a quarter wave vertical, but it does work, and it does work well. Plus, it's more elevated. You're significantly higher. Let's say this is near ground level, which mine is not. Mine is 10 foot off the ground. This gets you to, near about 40 feet off of the ground. With a quarter wave vertical, you're only looking at about 6 feet above the ground. 16 feet above the ground. So is it worth it? Yeah, possibly so. Well, so I would say if you need something like this, it's worth building. You can't go wrong. It's not that it won't work. It just depends on your application that you're trying to do. So Now let's go to the radio and let's see if we can hear anybody on there. Band conditions are not very good today, but let's see if we can find some conversation going on and switch back and forth between this antenna and the quarter wave vertical and see how they compare. So let's go do that right now. All right, so let's tune around here and see what we can find. And I'll try to hold the camera on the screen stable. Let's see what we can find. As I said, band conditions are not very good today, so we may be limited on what we can find, but let's try. Let's find something a little bit weaker. Okay, so right now we're looking at the quarter wave vertical. It's about S6 or S7. So let's switch to the half wave. So we drop down to about a S6, S6 and a half. We'll go back to the quarter wave. We've got about a S7 roughly. Back to the half wave. Well, that's a different person talking. About a S6, S6 and a half. So you can see that there's a little bit of difference, but it's not significant. And it does work. Let's go back to the quarter wave. There's the half wave. I think this guy said he's in Los Angeles. S4, S5. Go back to the half wave. S5, S6, maybe. So there's a little bit of difference in the reception. In the contacts that I've made using this antenna, there's about the same amount of difference in the receive level at the far end when I'm transmitting. So anyway, it works. It has a purpose. If you don't want to deal with radials, if you want to get it higher one way or another, the antenna higher one way or another, it may be worth it. So go for it, give it a try. If you like this video, give it a thumbs up, share it with somebody you think it might help. And if you like, subscribe, and we'll have more videos coming up. So until the next time, we'll see you later. Adios.